Okay, so this is Chapter 9, Calculus Based. There's two things in Chapter 9 that could be calculus based. The one that they have the most problems with, not problems, but exercises with, are basically like we did with linear acceleration, except it's with angular acceleration or angular displacement instead of linear displacement. So remember that we've already talked about this in class, but for angular situations we have that the angular acceleration vector is defined as the derivative of the angular position vector with respect to time, and the angular acceleration vector is equal to the derivative of the angular velocity vector with respect to time, or the second derivative of the angular displacement vector with respect to time. So you can go that way, or you could say that the angular angular velocity vector is the integral of the angular acceleration vector, and the position vector is equal to the integral of the angular velocity vector. So you can go either way. Start with the acceleration, go to velocity, go to displace or position, or you can go the other way. So when you look at the problems, you typically are either you can be given theta as a function of time. So, and it doesn't have to be just one dimension. It could be you could make it up into different components that are in the three component directions in the x, y, and z direction. So you could have like theta sub x of t times the I unit vector plus theta sub y of t in the j direction plus theta sub z in the of t in the k direction. Now, if it's one-dimensional, this is probably the one that it would be. It would be the one that's perpendicular to the I and j directions. Because remember, these vectors are going to be perpendicular to the plane that's associated with these things. So let's just make up a few problems just to show you how it works. So let's say theta is a function of time. We're just going to do this from a one-dimensional perspective. So you might have 2t cubed plus 3, and so this is if it's just, we could say it's k if we wanted to. Or we could just say theta as a function of time is 2t cubed plus 3, so the omega as a function of time is going to be equal to 6t squared, and alpha as a function of time is going to be equal to 12t. Okay, and these are all going to be, if this is k, these would be in the same direction. Now, in a couple of these problems, we're given omega, so you could go either way. If omega as a function of time was 5t squared plus t, then we could calculate the angular acceleration by taking the derivative of omega of t with respect to t. So that would be 10t plus 1. Or you could calculate the angular displacement as a function, or angular position as a function of time, by integrating omega of t dt. So we just put in omega as 5t squared plus t dt, integrate that, and you'd get 5t cubed over 3 plus t squared over 2 plus c. And when you integrate it, you need to have some kind of initial condition. So, if I said theta of 0 was equal to pi over 2 radians, so that's my initial position, that would mean that I'd start out up here, then I could use that. So I'd say, theta of 0 equals pi over 2 equals 5/3 times 0 cubed plus 0 squared over 2 plus c. So you get c is equal to pi over 2. So then, the particular solution would be equal to 5t cubed over 3 plus t squared over 2 plus pi over 2. And this would all be in radians. Now, one interesting thing is, what are the units of this constant? So if you think about what we need, we're just talking about units. If I call this A, this is A, and say this B would be a half, that's B. So A would be equal to 5/3, but the units would have to be such that the final answer is radians, which radians don't have any dimensions. So I'd have to have the units of 1 over seconds cubed, so that when I plugged in whatever time it was, I'd have seconds cubed divided by seconds cubed, which would just leave me with a dimensionless result. And the same thing is true for B. It would be 1/2, and the units would be seconds squared, so that when I evaluate the time part, time does have units, so you get seconds squared divided by seconds squared. Now pi over 2 is already unitless, so you don't have to do anything with that. So you'll see that in some of the problems where they give you the units, if they do give you units. Like 9-3, they don't give you units, but they do ask you to figure out what the units are, so that's kind of the process you use. Now, so that was the example. If they give you omega, how you could find alpha by taking the derivative, and you could find theta by taking the integral. So I kind of looked almost all the same, all the conditions. If you're given theta as a function of t, then you can calculate omega and alpha. The key thing here is that if this is, say, in the xy plane, if you have something, so here's our thing rotating in the xy plane. So this is say x and this is y. Then z would be, say, into or out of the board. So all the vectors associated with position, angular velocity, and angular acceleration are going to be along the z-axis. And if you're given omega as a function of time, you can. So the only one we haven't talked about is if you were given alpha as a function of t. So let's say it's 3t plus 2. And the units, alpha has units of radians per second squared, so the units for 2 would be 2 radians per second squared, and the units for 3 would be radians per second cubed, because I'd have radians per second cubed times seconds. That would give me radians per second squared. Okay, now, so if I asked you to find omega, you would integrate that. 3t plus 2 dt. So the integral of 3t is 3t squared over 2. The integral of 2 is 2t. And you add your arbitrary constant c. So this is your general solution. Now, to find the initial conditions, or to use some, it doesn't have to necessarily be at t equals 0, so let's just do one that doesn't have t equals 0. Let's say at t equals 1, omega of 1 is equal to 3 radians per second. So you would say, okay, omega of 1 is 3, so you get 3 radians per second is equal to 3/2 times t, which is 1 second squared, plus, and the units for 3 are, the units of this are radians per second cubed. So you can see what I'll have is radians second squared divided by seconds cubed. So I get radians per second, so that's right. And then you'd have 2 radians per second squared. So that's the units for 2 times t, 1 second. So again, there you have radians times seconds divided by seconds squared. So you end up with radians per second. And then you have your arbitrary constant c. So what we'd have is, so but the units are all right, correct. And the units for c are going to be radians per second as well. So you'd have 3 is equal to 3/2 plus 2 plus c. So what do you get? You'll get negative, c equals negative 1/2, I think. Yeah, because you'll have 3 minus 3/2 minus 2, which is 3 minus 2 is 1. So you get negative 1/2. So that's equal to c. So we can take our general solution and put in our particular solution, which will be 3. Let's go ahead and put the units in here just to be complete. 3 radians per second cubed times t squared plus 2 radians per second squared times t plus c, which is negative 1/2. So we get negative 1/2. The units for that are radians per second. Okay, now to find theta as a function of t, you're going to integrate omega as a function of t. So we plug in our expression for omega. I'm going to leave the units off here just so I have 3. No, I had a, did I forget a 2 here? Yeah, okay, so there's a 2. So I'm going to have 3/2 t squared plus 2t here minus 1/2. The whole thing times dt. So when I integrate this, I'll have t cubed over 3. So I'll have 3/2 t cubed over 3 plus, here I have 2 times t squared over 2 minus 1/2 t plus my arbitrary constant c. So once I clean this up a little bit, I'll have my general solution for the angle as a function of time. So it's t cubed over 2 plus t squared minus 1/2 t plus c. So that's my general solution. And then I can evaluate, use some initial conditions. So again, I'm going to do something else just to, instead of having 0. So let's say theta of 2 equals pi. Do I want to do that? No. It's not a trig function, so I'm just going to say, I'm going to use the whole number. So let's say it's equal to 5. So 5 radians. So you'd say 5 is equal to 2 cubed over 2 plus 2 squared minus 1/2 times 2 plus c. So we'll get 5 is equal to, here we have 8 divided by 2, which is 4. 2 squared, which is 4. 1/2 times 2, which is 1. So that's going to be 5 is equal to 8 minus 1 is 7 plus c. So c is equal to negative 2. So that allows us to then, instead of having a general solution, to have the particular solution. And I'm going to put the units back in there for the constants just a second. They don't change. The units for the constants don't change. And the constants are what's out in front of the variable parts. So you get 2. Okay. So putting back in the units, you'd have 1/2, and the units for this thing were somewhere over here. Let's go back over here. So this one was 3. 3 was the original one. So that was radians per second cubed. So we're going to have radians per second cubed here. Radians per second cubed times t cubed plus 1 radian per second squared times t squared minus 1/2 radians per second times t minus 2 radians. So if you look at the units, you got seconds cubed divided by seconds cubed, so you'll end up with the radians here. You have seconds squared divided by seconds squared. You end up with the radians. You have seconds divided by seconds. You get radians, and you get radians. So everything here works out correctly as far as the units are concerned. So that's the first part. The second part is calculating moments of inertia. So what you have to do is use integration, and they give you 2 examples in the book, and they say if you have constant density, it's just the density of the material times the integral of r squared times dv, where dv is a infinitesimal volume that makes up the 3-dimensional object. So they do a hollow or solid cylinder and a sphere. So with the solid cylinder, that becomes a disk, basically. If you go to page 290 in your book, if the length becomes small, then the cylinder becomes a disk, a solid cylinder, and then a hollow sphere or hollow cylinder becomes kind of like a hollow disk. So the things the examples in the problem that they do are from the calculus standpoint is to calculate the moment of inertias. That's section 9.6. So it says calculate the moment of inertia of a uniform solid disk, which is basically a cylinder. So you could just use the same procedure as the book. A lot of times when these things are round, it turns out it's easier to do them using different coordinates than x, y, z coordinates. Instead of using Cartesian coordinates, you can use some other coordinates.